All right, hi. So while the last person is sitting down, so I just got a question during the break, which I thought I'd answer, or at least I'll give my perspective on the answer. Different people might have different thoughts. So the question was, how do you approach a professor about summer research? And the answer is, well, there's various ways. So there's going to be advertisements for paid positions around kind of November, December, January, stuff like that for the summer. But also lots of people approach professors just like that by email or in person, asking about the research, like can I join your lab, stuff like that. So I'll give you kind of my perspective. Different people might have different perspectives. So the two things that I look for the most in terms of students who want to work with me are, one, have you done anything interesting in the past that was challenging and that was kind of similar to the kind of work that I'd want you to do with me in the lab? So any kind of personal project, school project, whatever, that was challenging, interesting, that you spent personal time doing, you were excited about, that's a good thing to tell the professor about. And I would actually recommend like bringing the stuff with you just to show, like if you're having a personal meeting, just kind of to show whatever it's a program, show a demo, like probably if it's in my field, it's probably going to be a program rather than a device or whatever. But anything like that, extremely helpful. So the other thing, and that's not an easy thing to do because, well, I mean, what I'm about to say is, if you understand kind of one of my research areas, like if you're able to talk in an interesting and kind of insightful way about an area of my research, that's a huge plus because most people absolutely cannot do that. So reading you cannot read probably any professor's papers, like all of them. If you pick an area that's kind of interesting to you and you start reading papers and you start thinking about them, starting understanding things more in depth, maybe kind of get interested, read more, that's a huge plus. That's something that the vast majority of students who approach the vast majority of professors don't have. So that's a huge plus. Of course, kind of just doing well in a professor's course is a plus. So by well, I mean, in particular, like if you solved like all the bonus problems or something, or if you performed like exceptionally well on the exam, of course, that could be noticed. In general, also having a good transcript and resume can't hurt. I would say the first two factors, to me at least, are the more important ones. There are different people with different perspectives. There are profs who just like look at the GPA. That also exists, but not just, but who kind of put a lot of emphasis on the GPA. So I would say very, very few students have like all four of those factors, right? Overall great resume and transcript, and also performed exceptionally well on the exam, and also have interesting personal projects, and also understand really well one of my areas. Like that almost never happens. But kind of any of those could help. If you have some combination, that could help more. I would encourage you to kind of not do kind of the statistical method of just like applying everywhere, which like people do, and then kind of a lot of emails get ignored that way. If you're really interested in doing research, well, part of it must be because you're actually interested in the actual area that this particular prof is researching. So reading up on their work is just natural. So as much as possible, I would encourage you to do that, depending on your area of interest. Like, you know, if it's like quantum physics or whatever, well, there is only so much that you there's only so much that you can read. You really need to be kind of at the graduate level to probably really understand cutting edge first. But as much as you can, I would encourage you to kind of take this approach. That's my view. Take it for what you will. It worked for me to some extent. So like when I was like applying, I would kind of go, well, actually kind of I printed my stuff out and I would just like go with a folder of my past projects and kind of to show whoever I was talking to. So I think that's an approach that you could take. Of course, like some other approaches I could just not take because my GPA was pretty bad. So I could not just like print out my transcript and show that. That would not have worked. So okay, so that's that. So I also wanted to show you some pictures. This is kind of the thing from last week with kind of the classic lather, rinse, repeat joke. I guess lather and rinse are like uncommon English words. So lather means like put the soap on whatever, and then rinse means rinse with water. So this is a fictional shampoo bottle. Not a real thing. But it has led to this classic joke, which I mentioned before. So this is like not the original. I think the classic joke is from like whenever. Okay. I actually went to the shoppers to investigate whether it's the case that shampoo bottles have those instructions. And the answer is no, they don't. So in fact, so this is something from Google Images, but if you go to the shoppers and you look at the shampoo bottles, if you have anything like that, this is what you see as you'll see like repeat if desired, which is different, right? So it's like while desired, rinse, repeat. So not actually an infinite loop. So while I was on Google Images, I also found this one. So that was kind of amusing. So this is pet shampoo. So remember to eliminate all escape routes well in advance. Once your pet is slippery wet, he or she is suddenly smarter and faster than you are. That's about my experience of trying to bathe a dog. Yes. And like it's like a running joke where like people just put whatever in the shampoo instructions. The other thing is the programmer would not have gotten stuck in the shower because in actual fact, nobody reads the shampoo instructions. So you can't get stuck in an infinite loop if you don't run the code. Okay. So the next thing I want to talk about is we haven't done the interview puzzles in a while. So I want to do the solution to last time's interview puzzle. And then I want to give you a new one. And along the way, it's just a useful example as well. So the last time, if you remember, so n factorial is this much. Times n. And the question was, what is the number of trailing zeros in n factorial? And the slow way to do this was to first compute n factorial and to then keep trying to divide it by 10 while you can. So if a number is something like this, you divide by 10 once, you erase 1 0, divide by 10 again, you erase this one, divide by 10 again, you erase this one, divide by 10 again, erase this one, and then it's not evenly divisible by 10 anymore. So the number of times that you divided by 10 is the number of trailing zeros. Right, so you can divide this by 10 evenly 10 times, 4 times, sorry. All right, so that was slow though. So just writing down n factorial for a large number is very difficult. So what can we do? So I'll introduce some notation here. So let's say that m is n factorial and want to know the number of zeros at the end of m. and the number of zeros is going to be k. All right. So here's the trick. So I'm going to say, okay, so the approach before was n factorial. Well, it's equal to this 1 times 2 times 3 and so on. But we can move stuff around and say that that's equal to a lot of tens times whatever. Right? So you can factor it like that if you want. You can factor anything. So how many tens? Well, k tens, because there's k trailing zeros, k tens at the end. Right? So 10 is, of course, 2 times 5. Like this. Times, again, whatever. So at this point, you will notice that the factors of 2 don't actually matter. And that's because there is always enough factors of 2. You're asking how many factors of 10? And the answer is, well, as many as there are factors of 5. Why? Because in this product, 1 times 2 times 3 times 4 times 5 times 6, like you multiply by 2, that's a factor of 2. You multiply by 4, that's 2 factors of 2. Multiply by 6, that's another one. By 8, that's 3 factors of 2, and so on. There's a lot of them going around. Factors of 5 are rarer, right? So just 5, 10, 15, and so on. So the limiting factor here is how many 5s. So I'll just rewrite it as a bunch of 5s times whatever. And the number of 5s in this equation is, if I put in as many 5s as possible in the left factor, is the number of zeros at the end, because the number of factors of 5 is the same as the number of factors of 10. Because there is a lot of factors of 2 going around, you can always find a factor of 2. All right. So, okay. So we still haven't answered the question. So the question was, well, how many trailing zeros? So we said, okay, as many as there are factors of 5. So how many factors of 5 in the number m? So the answer is, well, the answer is complicated, but I'm looking now from you for a wrong answer that's kind of right. Anyone? No pressure, it will be wrong. Yes. No? Okay. Well, I mean, sure, but then you have to get the prime factorization. So I'm looking for something simpler. I mean, you're right. Like, you can do the prime factorization, that will tell you the answer. Yeah. Well, I mean, I think you know the right answer. I'm looking for the wrong answer. Can you give me a wrong answer, please? Like, what's like a lower bound that's simple to compute? Yeah. Well, yeah, but well, I mean, yes, like the number of factors of 10 is the same as the number of factors of 5, but we don't know either one. Yeah.
Just first out how many like numbers in the series has 5 as factor, then we go from there.
Sure. And how many of those are there? So if we look, yeah. The closest power of 5. Well, no, because a power of 5 is like very different from m, possibly, right? Yeah. Divide by 10 and multiply by 2. Yes, also known as divide by 5. Yes, that is the answer that I was looking for. So yes, so just divide m by 5, and that and that is gonna be kind of the right answer. Because like what you're doing, you're saying, well, this is one factor of 5, and this is another factor of 5, and this is another factor of 5, and so on. Right? So every fifth number in this product contributes at least one factor of 5. So every fifth, how many of those? Well, m over 5. The issue is that this is not all of them, right? So this is not all of them because there is also times 25, and there is also times 50, and there's also times 125. And 25 contributes 2 5s because it's times 25 is like times 5 times 5. And then times 125 is times 5 cubed, right? So how do we count all of that? And I think someone said the right answer, right? So you have this, and then on top of that, every 25 contributes another factor, right? So every 25 contributes another factor. So how much is that? Well, every fifth element of the 5, 10, 15, and so on. So it's this much divided by 5 again. So this is like 25, 50, 75, and so on. So that accounts for kind of the squares. But then every 125, so 125, 5 cubed, we contribute 3. So we undercounted those. We counted one of the 5s when we did every fifth, and then we counted another one of the 5s when we did every 25th. And now we need to account for the third one. So every 125. So this is 5, by the way. So that is going to be this much. And then every 625. So 625 is 5 to the 4th. Every 625, there's another factor that we didn't account for yet. So just add that in as well. And so on. And then 5 to the 5th, I don't know, but it was just on the screen. So whatever, this is 5 to the 5th. Right? So every 3,125, there is 5 factors of 5. Right? And the reason we are just adding, so we're never saying plus 5 times, is because, so for 3,125, we counted one contribution from here. So this was every fifth, including 3,125. And then every 25, we added one more. So it was another factor for 3,125. And then by the end here, like if we are undercounting every 3,125 by 1, well, we just add one more here. And that would account for the factors that are contributed by 3,125, 3,125 times 5, and so on. Times 2 of them. So, okay. So that's like that. So now one kind of thing that I would recommend is just decompose this problem into 2 parts. So one was, what's the answer? The answer is, well, it's this much. The other part is, forget everything we set up to now. How do we compute this expression? So especially in the beginning, it's a very useful skill to just say, okay, like I wrote down what I need to compute. Now I free memory in my brain for how do I actually write it down in Python so that it computes it without thinking about factorials anymore. So how do we do this? Well, the basic thing is, well, we just compute this, and we compute this, and we compute this, and we add all those up. right? So the basic technique for adding stuff up, if you want to, for example, sum a list or something. What do? You say result initially is 0, and then you go through every element of the list and you update the result. And then by the end, the result is the sum. So in the same way here, we'll start with a result that's 0, and then we'll add this guy, and then we'll add this guy, and then we'll add this guy, and so on. So, okay. So this will be trailing zeros n. So, sorry, so all of this was n, by the way, not m. Oh, it was m. I'm sorry. So all of that stuff was, of course, n rather than m. How many zeros in m was, well, divide by 10 as many times as possible. The problem is we don't want to compute that. So, okay. So what we'll do is we'll say, okay, all right, so result is initially 0. And then the current term, we'll say, is currently n over 5. And now we'll do a loop. So what's the loop going to be? The loop is going to be, when do we stop this? When do we stop this madness? Well, we stop when there's no point anymore. So if n is 2000, then there's not going to be every 3125th term. How would that show up there? Well, the term will just become 0. So we'll keep going while current term is greater than 0. Sorry, over there by the clock. Hello? You're being loud. Hi. Okay. So we'll say while current term is greater than 0, we'll add current term to result. And we'll divide current term by 5. All right, so what's going to happen here? So first current term is going to be n over 5. And then current term is going to be n over 5 over 5. And that's going to be this and so on, because we divide by 5 at every iteration. And we just add it into the result. When do we stop? When current term becomes 0. Will it become 0? Well, yes, because divided by 5 integer division always makes the number smaller unless the number is already 0. Yeah.
Then how do we know to use the double slash dividing rather than single one in this?
Yeah, so that's a good question. So what we're saying here is we want to know how many terms appear every 5 times. And the answer is an integer, right? It can be like a fractional number of times doesn't make sense here. So if we have the numbers 1, 2, 3, 4, 5, 6, 7, and we want to know how many times every 5th element appears, the answer is 1. Right? So if it's this much, how many times every 5th term appears? Well, the answer is, well, it's 5 and 10. So how many times? Well, approximately 12 divided by 5, but less than 12 divided by 5 if it's a fraction, because you might have stuff left over that's not reaching the full 5. All right. So that's what, so kind of one answer is, well, like the answer has got to be an integer because we're counting kind of whole things where fractions don't really make sense. The other thing is you just look at the application, like what are we actually computing? Like how many times every 5th element appears? And the answer is, well, approximately 12 divided by 5 in this case, but rounded down. All right. So that's this, and that's the answer. Right, so there's not kind of a neater formula there. Let's see what Discord is saying. Why is it that you can print if it's by commas? Well, because you can give print several things and separated by commas, and it'll print everything. So this is what's called a variadic function. Spelled like this. So this means a function that can take several parameters, and the number of parameters is not necessarily pre-specified. You don't have to know this term. I probably didn't pronounce it right. I probably have not ever heard it pronounced. So that was the first time. And now it's on YouTube. And given that I'm like a U of T prof, maybe people will like repeat after me, which they really shouldn't in the case of English pronunciation. I often get it wrong. Anyway, the point is print can take one argument or two arguments or three arguments, and they can be of any type. It'll just print them in turn. That's just what print does. I'm not going to cover how to do variadic functions in Python. You can, however, Google for it. Okay. So, okay. This is that. Other questions? All right. So I want to do the next interview puzzle. So I call it the missing K problem. And the setting is like that. We are given a list of integers L. The list has elements 1, 2, and so on up to N, except that K is missing. And the task is find K efficiently. And I'll talk a little bit about what efficiently means. In this class, I often get the question, like on the midterm, do I have to write things efficiently? Well, no, on the midterm, no. Later on in the class, we'll introduce some notions that are kind of like rigorous definitions of efficiency. And once we've rigorously introduced efficiency, then I can ask for something that in some kind of according to the definition is efficient. So far, we haven't done it, so I'm obviously not going to do that. So, okay. So an example would be something like, 5, 1, 3, 4, and then 2 is missing. Something like that. So what I'm going to do is I'm going to write an inefficient version. And incidentally, it's also just a good example to do in class anyways. And I'll leave it to you to think about what you can do efficiently. So here's what I'm going to do. I'm just going to say, try every possible solution. Return K if it seems like it's missing. So in order to get all the possible solutions, so those would be 1, 2, and so on up to N, I need to know what N is. So if I have a list of length of L, what is N? Anyone? So a list of length of L contains every element from 1 to N except for 1. How many elements? Yes. Yeah. Yes, so the answer to the last question I was asking is length of L, well, that's n minus 1. Why? Well, because there's n elements from 1 to n and 1 is missing. So the number of elements in the list is n minus 1. So if the length of L is n minus 1, it must be that n is length of L plus 1, just because of algebra.
Assuming we're not allowed to use like sort.
You are. It's just that. That's not the most efficient thing.
Okay.
Okay. So n is length of L plus 1. So what I'll do now is I'll just try every possible k. So I'll say for k in range 1 n plus 1. So remember, 1 n plus 1 means up to but not including n plus 1. So I try 1, 2, 3, and so on up to n. And then if k is not an L, so it's missing, then that's the answer. I'll just return k. That's it. Right? So I'm saying k is 1, then k is 2, then k is 3, and so on, up until the time that k is equal to n. And then if k at any point is not an L, then I have my answer. I found my missing k. So writing code like this should give you a little bit of anxiety because the return is inside the conditional. So that means that you got to think, oh, like, but what if I never get to a return? Is that bad? The answer in this case is no, because here we just said that L is a list of integers with one of them missing. So you just assume that the input is valid. If the input is valid, then there is a k that's missing, and you'll find it. If L is not a valid input, so for example, it's integers, but it's not in the format 1 through n with one of them missing, then it might be that you'll never get to a return, right? Because, like if all the elements are like negative or something, I don't know, then it will be weird. In this case, you will get to a return, but not always guaranteed, right? So what happens if you never return? Well, it'll be return none, right? So a function that doesn't return anything and you get to this point, it's as if you had said return none. None is the special value that's, among other things, just returned if nothing is returned from the function. Yeah.
And the length of L plus 1, and then you have the range of 1, n plus 1.
That's right.
Would that be length plus 2?
Or, I mean, yes, like mathematically, sure. So yeah, so in this case, it doesn't matter, right? Because whatever, like it's like, in fact, what's going to happen if L is like invalid but it has a length, then 1 is just not going to be in there, possibly, for example. So you'll just return that. It might not make sense as an answer. But here you're kind of assuming that the input is valid. In general, if it's production code, well, like you want to make like very sure that you are not kind of missing out on any edge cases or something. So you might check that L was a valid list, or you might say, I definitely tested the code that will ever use this function, and I'm sure that this code will not call this function if the situation is invalid. But this kind of thing should give you kind of a little bit of anxiety. In this case, it turns out to be fine. So, okay. So that's the missing k. So I want to now talk about something new, unless there's questions. All right. So I want to now talk about something new. So, or kind of new. So this is called nested lists. Loops. So kind of nested just means a thing within itself. So in this case, like loops within loops. So here's a simple example. So I'll do for I in range, let's say 1 to 5, and then I'll do for j in range, and I'll explain in a second. Let's say 6 to 8. And I'll just say what I is and what j is. So here's what happens if I run it. It's like this. So here's what's going on. One way to think about it at least. So I'm saying for I in range 1 through 5, right? And then I'm just saying run this. So when I is 1, I just run the highlighted part. And then when I is 2, I just run the highlighted part. Then when I is 3, I run the highlighted part, and so on. So let's imagine that just I is just set to 1, and I'm just running this thing. What's going to happen? Well, j is going to be 6, and then it's going to be 7. And in fact, that's exactly what you see. So I is 1, and then first j is 6, and then j is 7. I stays 1. Of course, because I is 1, and then you just run the highlighted part. And then that iteration is over. So then I becomes 2. And again, like I is 2, it's fixed, and you just run the highlighted part. Make sense? And that's what you see. I is fixed, so I is 2, and j goes from 6 to 7. And then I is 3, and j goes from 6 to 7. And then I is 4, and j goes from 6 to 7. Make sense? So what's an application of this? So you'll see multiple, but one obvious thing is you just say, well, like if I let I go through the entire range and let j go through the entire range, what are all the combinations of the different i's and j's? So one thing that you might think is like, I'll try to like print like all the possible passwords of length 2. So what can I do? Well, I can say, so let's say that this is the alphabet, like a short alphabet. So I can say for letter 1 in alpha, and then I can say for letter 2 in alpha, and I'll just print letter 1 plus letter 2. So what happens is letter 1 is going to be A, and then B, and then C, and then D. And then in here, so when letter 1 is A, I just run this, meaning letter 2 is A, then B, then C, then D, while letter 1 is fixed at A. And then letter 1 becomes B, and again, letter 2 just goes A, B, C, D, right? Because letter 1, when it's B, I just run this. So what happens when I run this and letter 1 is B? Well, it's going to be B plus letter 2, for letter 2 being A, then B, then C, then D. So you run this, and that gives you all the combinations of all the letters. And you can do more of this, right? So you can say for letter 3 in alpha, and then for letter 4 in alpha, and just print letter 1 plus letter 2 plus letter 3 plus letter 4. And that's going to be all the possible combinations of all the letters in the small alphabet A, B, C, D. Right? So why does it work? Well, we kind of made the argument, and we'll make the argument again next time. So you just do this, and you make it so that letter 1 plus letter 2 is all the possibilities. And then this happens multiple times with letter 1 fixed and letter 2 fixed. and you just run this. When you run this, what happens? Well, letter 1 plus letter 2 is always the same. And then letter 3, letter 4 is all the combinations. So together, it's all the combinations of 1, 2, 3, 4. And that is in fact what you see. So I'll explain this. So I'll explain this multiple times. So next time it's going to happen on Wednesday. Now I want to switch to another interesting topic, which is the midterm. So all the past midterm papers are available on the course webpage. So you can also look at the solutions. In the solutions, you also see the marking scheme usually. So I don't always put it up, but usually I do. So if you are wondering, so every question is different, but if you're wondering how approximately how things are graded, there is like a pretty detailed answer. So I just want to go through the latest paper and just kind of mark out what's happening with some of the questions. So the midterm this year is actually a little bit earlier than usual. So there's going to be a little bit less material than usual, just because we won't have covered like all the material that we would have covered by October 31st or whatever. And usually, like it's like, I think it's, I don't quote me on what it is, but it's like not the 31st this year. So I believe like 5 days earlier or something around that, but yeah. So a lot of the questions, the way they're composed is I look at the lab questions and I say, what would be kind of, if the person has done the lab, what would be a reasonable question to ask that would kind of test knowledge skills that are related to kind of that particular lab question. Of course, can't do it with every lab questions. There's too many of them, but that's an approach that they take with several of the questions on the midterm. Some of them the same with lecture, and then maybe sometimes one that's like more creative problem solving. So let's look at question 1. So take the number n, return a list of all the perfect squares between 0 and n. So a perfect square is a number like 4, 2 squared, or like 9, 16, 25, and so on. Right? So how can we do it? Well, one way to do it is the same approach that we took to the missing k problem. Just go through every possible integer and ask, is it a perfect square or not? If it is, add it to the result. If it's not, don't add it to the result. Right? So this is kind of a combination of technique. So it's a little bit similar. So kind of checking whether a number is a perfect square is kind of similar to checking if a number is prime, right? So like one easy way to check if it's a perfect square is you can just say, okay, like if you take the square root of the number and then you round it and then you square it back, is it the same as the original number? And if it is, that must be because it's a perfect square, right? So usually you would get a fraction, then you round it down, so you square it back, it's not the end. And one simple approach you can do is just do this, and then you would just say result is initially nothing, and then, so n is unfortunate because n is our upper limit. So this would be in range, so n plus 1, because we want up to including n, and then we'll say, if that is the case, then add I to the result, and we return the results. Done. All right, so something like this. So this is a combination of this idea of starting from scratch in terms of the answer and building the answer up, and checking whether a number is a perfect square or not. Using, for example, this kind of trick, there's multiple things you can do. not the only way to approach this. So, okay. This one is easier. So here you just need and I should say kind of naturally, because we haven't done a lot in like week 1 and 2, the kind of the latest several weeks are going to be kind of more heavily emphasized in the midterm, just because like what you're going to ask about week 2 or something, right? So after you've done the lab for this week and the lab for next week, you will not do the lab. Well, yeah, so I think actually there's no lab the week after next. But after you've done the lab next week, you'll have kind of much more practice with a lot of the questions that you'll see on past midterms, especially given that past midterms were usually a week later in the term than this year. But anyway, how do you do this? Well, again, it's the same approach. So you start from scratch and you build the answer up. So here we need a product of this. So the result initially is 1. So here we've done it with factorial. When it's a product, it makes sense to start with 1, not with 0, because you multiply 0 by anything, it's still 0. So those answers are also in the solutions anyway, might be a little bit different. And you return results, something like that. All right. So again, kind of it's kind of a combination of those ideas of starting from something and then building the answer up. And in this case, you also have to know how to go through elements of the list. So like for E and L. So this one I'll talk about next time. So I want to say that question 4 is not really relevant, and question 5 is that. So question 4 might be, depending on what you cover. Question 5 definitely won't cover, almost definitely won't cover. Question 6 is interesting. I'll talk about it next time. It is relevant. You can do it now. All right. Thank you very much. I'll see you Wednesday. Sorry.